Greetings and salutation. My name is Shazly bin Shamsul Fansury, alongside with my group members, Zakwan and also Lue. So today, our group 5 will present to you our topic for this subject. So the topic that we picked for this subject, programming bioinformatics, is prediction on stomach cancer prognosis from gene expression data using support vector machine. So from the problem background, we can see that cancer is a common and a fatal disease, and we can see during this day, cancer can be occur and disease can be spread by environments, individuals, and also animals. Stomach cancer can be cured by removing them in early stage, but it's hard to diagnose because of the size of the cell. And if the cancerous tumor increases, uh, there's a chance that a lot of tissues can lead to failure and can cause the body to um, dysfunctional. Prediction of stomach cancer prognosis is very necessary in cancer research to facilitate the subsequent clinical management of the patients. Using the SVM can examine a gene expression from tumor and also fluid, from a tumor sample or from a peripheral fluid. Moving on, problem statement. So the problem statement is that prognosis process of stomach cancer is very challenging because of the implementation algorithm and the size of the data is very large, and there's a lot of variety and the types of genes in a tumor cell. Tumor cell in different people can mutate in different sequence of gene expression. By using SVM, SVM can analyze big data of GEO, which means a software that we can examine a lot of data sets, stomach cancerous cells to build up a predictive model. So the next one is that objective. So the objective of this project is to predict a good accuracy for stomach cancer prognosis. SVM will use stomach cancer dataset to distinguish functional class or not. And the other one is compare stomach cancer cell to improve our classification accuracy. Hence, the scopes is that it beneficial in predicting stomach cancer diagnosis and also prognosis in order to create a probability of recovery and recurrence and the ratio of the treatments. The support vector machine method is applied in the stomach cancer prediction, and most of the cancer prediction use SVM. Moving on to the other one is the flowchart that we propose on the progress tree is that as we can see, we start from the above and then we down to the research to gather information on the stomach cancer. Moving on to the stomach cancer dataset, which means the symbols symbolize the database information. So we gather around, then we move to pre-processed data. Then we feature the extraction of the data. After that, then we test the data using SVM, support vector machine. Then we analyze the result. And if the decision result says no, then we need to redefine our model, redefine our information back on top of this, and then we do again research and data set, then moving forward. And if the decision says yes, then we documentize the information for the data and for the report. After that, we will finish. That's all.
Hello, my name is Guo Ming. In this project, I will be presenting our progress to importing dataset, data wrangling and preprocessing, and progress for model development. In progress 2, basically we use pandas to pre-processing the data. First of all, the dataset we use is a sample of genes obtained from an individual. The original dataset having information about gene ID, name, its locus, row count, and the FPKM value. Fragments per kilobase of transcript per million fragments map FPKM is a biologically normalized data measuring the presence of exon and considering length and depth of a gene. At first, we find out the missing value in the dataset. Since every gene is unique with its length and depth, We do not override the missing value with mean or median, hence we drop it. Currently, the locus is an object type variable. To find the real length of a string in number, we split the locus to position, start length and end length. There is unknown data causing missing value of dataset, so we drop it. After split the locus to three columns, we have to change the data type as int so it can be used in numbering system. After we know the end and start length, we can know the length in kilobytes. This process is important for us to generate normalized data other from FPKM. This is the type, shape, and size of the dataset. We do not really use the gene ID, locus, position, and length not in kilobytes in our future modeling, so we drop it. Apart from FPKM, there are other types of normalized data such as RPKN and TPM. Calculate using length and gene count by using different formula or algorithms. Even though FPKM, RPKN, and TPM are biologically normalized data, the scales or difference between gene samples are still very big. So we do Z-score normalization for count, FPKM, RPKM, TPM to control a proper scaling within a dataset. As we can see, the minimum gene only 0.199 kilobytes, but maximum is 2304.996 kilobytes. In data binding, we categorize the data to separate columns. Each of them represents a gap. Since we are using SVM linear regression method, we do not really use the categorized data sent to indicator variables. Instead of data binding, can produce a get. Indicator variables indicate the value is true or false by using 0 or 1 number only. The main important features used to indicate our model development are the counts, length, continuous data, and normalized data.
So briefly on progress 3, we propose to you that our flowchart that we use. So now I'm going to show you our statistic findings, which consists of mean, median, and also standard deviation. So the first one, as usual, we need to have library packages. So library package, we use numpy, pandas, and also skippy. And the first one is we define first the file that we need that we already created, which is we use CSV file. So CSV file stands for comma separated values. Comma separated values, which means is a text file that specific format which allows data to be saved in table structured format. So first we define, and this is the file that we define and that we read, leandata.csv. So this is the output that we gathered after we successfully define the file. So moving on is we define the sum for the data sets as usual. Define first df.sums. So as you can see, this is the output after we successfully define the sums of the data sets. And moving on is we define the median. In the median, because this is statistics findings, so statistics finding must consist of median, mean, and also standard deviation. So we define the median of the data sets and we successfully gather the output. So as you can see, this is the output. Then we define the mean of the data set. This is the output after we gathered. So you can see there's a ND frame and also add numeric operations for mean. Next is we define the max value of the dataset, because in the in the file or before CSV, yeah, in the CSV file, there's a lot of values, so we max it and then we take the max value, the maximum value. So this is the FPKM, RPKM, and also TPM. This is the max value of every information gathered, and we summarize it into one. So the next one is standard deviation, and this is the last one we define STD, standard deviation of data sets, because standard deviation tells us how to spread out our data. So we define first the data sets, and then the last one is define our variance for data sets. So this is the output. As you can see, this is what we gathered from our CSV file, and then we use finding statistics. And the last one is define describe. This is the last describe before progress 4. As you can see, this is the last output, RPKM, TPM, and also z-score, FPKM, RPKM, and also TPM.
For progress for model development, we mainly work on the FPKM, TPM, RPKM value to build predictive model, predictive gene count. The three variables are calculated by the raw count and length of genes by different algorithms, so we consider the three variables are independent and raw count is the dependent variable of them. First is the simple linear regression. Put FPKM as S, count as Y, develop model using fit. Finally, predict count based on the FPKM. This is the first 5 value. The intercept find out the intersection point of the linear regression model, and the coef find out the coefficiency of the linear regression model. Multiple linear regression is similar to simple linear regression. The only difference is it considers more than one independent variable to predict Y. Definitely, the result will be different, and multiple linear regression tend to have obtain larger C-intercept, as the normalized data is calculated by raw count. When count is 0, normalized data will be 0. We have a hypothesis that the smaller the value of C-intercept, the better the predictive model is. Furthermore, we can see the gap or the difference between predictions are very big. It is because every gene have different length and depth. To prevent a large-scale difference and error in model development, Z-score normalization can be applied to minimize the difference between each value. This is the linear regression tried with Z-score. We can see the prediction scales. The values are smaller and the scales are smaller. Next, model evaluation using virtualization. From the diagram, we can observe that the features are more focused and match in length when count and FPKM are very small. All normalized data, including Z-score, construct a similar pattern of model. The only difference is the scale of x-axis and y-axis become much smaller in Z-score. It can reduce the error and increase the accuracy of predictions. Next, polynomial and pipeline. Polynomial fit has the similar pattern with previous visualization, but the way of preprocessing data is different. Pipeline is a tool that allows different user-defined Python methods such as standard scalar and polynomial features to create a linear regression model. Finally, we have tried build out a common support vector regression model using the independent variables FPKN, RPKM, TPM, and dependent variables count. And also we have tried to build another model using Z-score. This is we train the dataset using train test split. The degree of inaccuracy in statistical models is caused by the mean square error or MSE between the observed and projected values. It evaluates the average square difference, whereas R square is a statistical measure that shows how much of dependent variables variance is explained by one or more independent variables in a regression model. R square measures how well the variations of one variable accounts for the variables of the second, as opposed to correlations, which describe the strength of the relationship between independent and dependent variables. Therefore, if a model R square is 0.5, its input can account for around half of the observed variations. In our case, R square value of both test sample would not reach 0.5, either the normal data or Z-score data. Its input cannot account for the observed variation. We might conclude that FPKM, TPM, RPKM are not really influenced by thin count only. There are another dependent variables. Moreover, the mean square error of both gene count predictions are greater than 0.5. We may conclude that the results are inaccurate. Finally, the prediction and decision making. The data are well distributed and more accurate by using Z-score. We can see the difference between test sample and prediction are smaller in Z-score predictions. From previous model development, we can see the smaller the value, the accuracy increase. In the case gene equal to 0, FPKM, RPKM, and TPM will be 0. A simple linear regression would be the best model to choose, building with Z-score normalized data due to its low z-intercept value and small scale, which is only 2.66, and by using multiple linear regressions is 5.1 at it. That's all for me. Thank you.
Hello, my name is Mohammed Zakwan Zakirin Razak, and now I'm going to present about the progress file. So first of all, for this code, this is for the protein function that will be used at the below later. That I will show after this, and after that we doing the train split and printing the number of the training sample and the test sample, which is for the training sample we get is 20,631, and for the test sample is 2,292. And after that we doing the linear regression fit with the data of FPKM, and we calculate the test score for the FPKM, which is this is the output, and the train data of the FPKM, which is this is the output. After that we use the cross validation score, which is we doing for the linear regression of the FPKM data with the 4 prediction number, which is this is the prediction number, and we calculating the average and the standard deviation of the estimation, which is this is the value. And after that we do the negative square error, which is with the 4 value above, which is this is the output. And next is we do the cross validation predict, and with the 5 prediction number, and the output also will be 5. After that we do the overfitting, which we do the fitting of the linear regression with the data of FPKM, RPKM, and TPM. Then we do the prediction using the training data with the first 5 prediction number, which is this is the output. And after that we do the prediction using the test data with the first 5 prediction number, which is this is the output. And after that we do the training training graph, which is distribution of plot of predicted value using the training data versus the training data distribution, which is the value is at 0. And next we do the distribution of predicted value using the test data and data distribution of test data, which is this is the value bar graph. And for the overfitting, we import the sklearn preprocessing, import polynomial features, and we fit fit our polynomial features with the data of FPKM for the train data and test data. And for the linear regression prediction, we do this for the fit of train, X train, and Y train with the first 5 predicted number, which is this is the output. And then we take in the first 5 predicted value and compare it with the actual target, and which is this is the value, the output of it. And after that, we display the training data, testing data, and the prediction function with the training data FPKM and test data FPKM, which is the output of it, the output of the graph, which is we can see on the training data, which is red, test data is green, and the prediction function, which is the line. We will see the output value, and we do the R square mean of the training data, and this is the value for the R square of the training data, and we do the R square for the test data, which is we got is the negative 213. Then we do the plotting a figure, which is for the to label the X label for order and Y label is for R square 2 with the title of R square 2 using the test data, which is this is what we get with the 0 with this maximum of R square 2, we decline to the 4. And we do the define a function for order and test data, then this is the code for this. And we do the regression, which is we compare the polynomial feature with degree 2, and we fit our train data and test data with the FPKM, RPKM, and TBM. Then we import the ridge from the SECB3203 linear model. Then we fit the train that X train with and Y train, and we predict the ridge model with the X train X test data with Y prediction. After that, we compare the first 4 predicted sample to the test set, which is the Y prediction 0 to 4, and test set also will be compared 0 to 4, and this is the first 4 value of the output. Then we import the QDM, and we with the alpha we set with the numpy array range from 0 to 1000. Then for the alpha we do the ridge model, we compare with the X train and Y train, and we do the calculation for the test score and train score, which is the final test score is 0.621 and train score is 0.618. And after that, we plot out the value of R square 2 for different alpha, which is for this is the value is on 0 for the validation and training data. And after that, we import grid search CV from the SECB model selection, and we including the parameter, and this is the random parameter of it, and we create a rich regression object, and after that we create a rich grid search object, and we feed the data of the FPKM, RPKM, and TPM. Then we do the estimator with the perimeter, and this is the value output of for the best rich regression. That's all for the progress file.